Hello everyone, welcome you all to my YouTube channel. So from today onwards, I will be discussing quantum mechanics in a simpler possible way. So for the time being, I am discussing with the simple harmonic oscillator. So without wasting our time, let's discuss. So let us consider a diametric molecule. Okay. So what are the possible motion it can have, right? Like it can have translational motion. It can have rotational motion. It can have vibrational motion, right? These are the main three motion that a diametric molecule can have. And for each of the motion, we have it particular model in quantum mechanics. Like for translational motion, we have particle and box model. Okay. For rotational motion, we have rigid rotor model. And today we are going to study the vibrational motion. Okay. So here what happens in vibration, the bond length is the variable we need to use to describe the vibration of the molecule, right? So we need to describe the how to quantum mechanically we can describe the state of vibrational motion. Okay. So to understand any system, we need to have the vibrational energy. Okay, we know to understand any system, first we need to have the Schrodinger equation, right? And before Schrodinger equation, we need to have the value of potential energy. Okay, because we have to plug it the value of potential energy in the Schrodinger equation. And we can remember that for PIB model and RR model, we have solved the Schrodinger equation by considering the V equal to 0. That's potential energy equal to 0. Can we think that what can be the value of potential energy in case of vibrational motion? Can it be 0? No, it can't. I can prove you, right? Wait. See, what does it mean by potential energy? Potential energy means when you bring a body to a certain height, it has some potential energy, right? When you compress two molecules, when you stretch two molecules, it has the potential energy. So here potential energy can't be 0. We can prove it by Heisenberg uncertainty principle also, right? If potential energy is 0, it does mean that we know the relation B equal to half kx square. I will discuss in this video only. So, and x is nothing but the change in the distance. If V equal to 0, it does mean that this value is 0. If this value is 0, then that does mean that x is known. Okay. It means del x equal to 0. That the uncertainty in position is 0. And B equal to 0 means molecule is not vibrating anymore. It means the uncertainty in the momentum also 0. But this is not possible, right? We can have the del x equal to 0 and del p equal to 0 at the same time. This is going to violate the Heisenberg uncertainty principle. So B can't be 0. This is clear? Okay. So unlike rotation, suppose I am rotating, this is diametric molecule, okay? And this is the axis, suppose, and I am rotating up to a certain theta. Okay. So unlike rotation, or I should not really expect the energy of the molecule to be different if I just place the molecule in a different orientation, right? Like this. Or translation, if I just move the molecule to a different position. In this case, we can't expect the V to have a value, right? This we can certainly assume that V is 0, right? Okay. Okay. So if I draw a qualitative picture of what the potential energy will look like if I change the bond length. So if I have a diatomic molecule, okay, so when you stretch the molecule, right, we are stretching the molecule right here, okay, then I have to put energy to stretch the molecule, right? So energy is going to increase. Similarly, if I am compressing the molecule, then what happens? I have to counteract the repulsion between the molecules, so I have to give extra energy. So whether you stretch the molecule or compress the molecule, energy is going to be increased. So let me draw the graph for this kind of situation. Suppose this is the R equilibrium, okay? That is the minimum energy position of the molecule. And okay, so if I am stretching the molecule, the energy is going to increase and will become 0. Okay. Similarly, if I am compressing the molecule, it's going to increase. It does not come to 0 because I am compressing the molecule and there will be repulsion between the nuclei and electron cloud between the two molecules, right? So this can't be 0. This will only rise up. Okay. So this is a general step qualitatively I have drawn by taking into consideration the situation that is stretching and compressing. But the problem is that it's not actually know how to write an equation for this kind of curve, right? And if I could know this, it would be quite complicated expression. And if I insert into Schrodinger equation, the equation is going to be very difficult to solve without any powerful computer system. So what physical chemist does in this situation, they often consider a model by taking into consideration some approximation and try to solve the problem. Suppose instead of this curve, I am drawing another curve like this. Okay, so we need to think about a simple problem that we will able to solve, right? So you can see this curve, the new curve, and this curve is already known to us because this is a parabolic curve, right? And we know the equation for this curve. This is y equal to half kx square, where k is the variable, x is the variable, sorry. And if here x is nothing but r minus r equilibrium, okay? can solve this equation, and we know the relation already. Okay, V equal half k, so that's potential energy of this equation, of this curve. And you can notice here this new curve is not exactly different. So to carry out the calculation in the lower region, you can see this is exactly superimposing with the existing curve that we have already, right? So we can calculate the potential energy, or we can solve the Schrodinger equation by taking into consideration this simple harmonic model, right? Because in the lower level, it is exactly what we should expect for a molecule to have. That is, when you state the molecule, this energy is going to increase, and when you compress the molecule, then also the energy is going to increase. So by solving, we have to use this potential energy in the Schrodinger equation, and the rest of the things we will discuss in the next class. Thank you.